Okay, good morning. One last final topic is basically small signal analysis of CE amplifier. So let's look at that. Let's see. Okay. All right, so we're going to apply the hybrid pi model to analyze the CE amplifier and then derive the gain of this amplifier. Okay. From the lab, you already know what the expected gain would be, like ratio of the collector resistor to the emitter resistor. So basically, this was obviously a design that was done decades ago. This is just to show students how you can use a appropriate model or basically any kind of model to derive our equations. Okay. So here we have a voltage divider bias circuit. And these resistors, of course, are R1 and R2. We are going to use the small signal model. Specifically the hybrid pi model. And the gain equation is to be determined. Okay. So V out, of course, is taken here, the collector. Input V in is here. In our lab and in other experiments, we have a bypass capacitor also across the emitter, but for now, we'll ignore that. So in a small signal model, DC sources are reduced to 0. So VCC is connected to ground. Or actually, not VCC. The node at the top is connected to ground. And so the circuit would look like this. In the previous slide where we saw how we can signal analysis right here. This one. Right? Because the collector resistor is connected to ground, comes in parallel with the output. So that's the circuit we need. So if I was to draw this, I have a BJT, emitter resistor, and then I would have RC. So right now we are simply applying small signal analysis to the externals and just redrawing the external circuit. The BJT hybrid pi model will be in the next step. So this is our AC input V in, R1, R2 in parallel. Yes. Yeah, for AC, we reduce the DC sources to 0. For DC analysis, AC is not considered for DC. For yeah. Yep. We reduce to 0, meaning voltage sources are replaced with a short circuit, meaning that node will be directly connected to ground. So now that we have this, we will replace the BJT with its hybrid pi model. Okay. Everything else will remain the way it is, including the resistors, but the BJT will be replaced with the hybrid pi, meaning R pi input resistance, RO output resistance, and a dependent current source at the collector. Okay. So R1 and R2 can be reduced to the base resistor RB. And then here we would have our hybrid pi model, R pi, emitter resistor RE. So let me go ahead and write this down. 100. This is RB, which is R1 parallel R2. This is R pi. And then at the output, we have RO. I don't have enough time to get through everything. Yep, coming up. And then lastly, here we have RC. Okay. So 1, 2, 3 external resistors accounted for, and then internally we have R pi and RO. All right, let's the current and the voltage markings. So now here we have base voltage being applied. V in is being applied here, which of course comes in parallel to RB. We can state IB base current is flowing in this direction. IE flowing down, and IC would be flowing up because this was the top of our resistor. Here we can write IC flowing up, and then output plus minus VO. Okay. This current can be GM VBE in terms of voltage, or it could be bit IB. Oh, not case, lowercase. Everything is lowercase. Let's see. We have IC, IE, IB input current, everything's there. Okay, we can begin analysis. Standard KVL applications. We'll apply KVL in the input loop. Input loop in this case would be here, which includes the base resistance RB, emitter resistor RE, and R pi. Voltage drop that occurs across all three resistors is due to IB and IE. So I can write V in directly in terms of, so let's say apply KVL. (1155) input loop. We have V in is equal to IB R pi plus IE RE. Okay. Now the goal, of course, for us is to obtain the gain of the circuit. The gain is the ratio of the output voltage to output, so the input voltage, meaning VO over V in. That is the goal. So one of the ways we can do that, so again, the goal is to determine VO to V in. One of the ways we can find this is by finding currents and then finding voltages. Another way is we can find impedances, if we find output impedance and input impedance. And so in this particular case, that's the route that we're going to use. We're going to determine, not determine, but we're going to use equations for impedances from the output and the input side. So ZO or Zin or Zi. And Zin would actually simply be RB in parallel with this base resistance. So if we say, looking into the base of the BJT, what is the impedance? And we can state and label that as ZB. Okay, ZB is the impedance looking into the base. And from the small signal model, it comprises of R pi and RE. Okay, yes. It's not the gain. I'm saying one of the ways we can use to find VO or Vin is to find the ratio of the impedances or just work with impedances. Because impedance is voltage divided by current. So if we can find impedances, that is one pathway we can take to determine VO or Vin. So in this case, as I said, if you look into the impedance of the base, ZB, we can write this equation and modify it to obtain that value. So here, we can write Vin is equal to IBR pi and replace IE with IB. So it would be IB beta plus 1 times RE. IB is the input current. So if we take it on the other side and we write Vin or IB, I can write R pi plus beta plus 1 RE. Okay. All right. So that's the input current and the input voltage being applied, which would be the impedance of the base, ZB. So I can write, if I make an assumption, not an assumption, but R pi typically would be far, far less than beta times RE. So RE is 1 or 2 kilo ohms, and your beta is about 35 to 100 typical values. And your R pi is going to be far less than beta plus 1 times RE. Okay. And so I can simply state ZB is approximately equal to beta times RE. All right, about 30 seconds left. Just stop here. And then I can find the input impedance of this circuit, RB parallel ZB. Okay. Again, ZB is the input impedance, not input impedance, the base impedance or impedance seen from the base. And Zin is the impedance seen from the input terminals. Yes. Why is it reasonable? Because that would be it. Yeah. R pi would be typically less than beta plus 1 RE. Yes. Zin would be from the terminals. Looking at it from the terminals. Okay. So this would be the input impedance. We stop right here and look at output impedance on Wednesday. Won't take more than 10 minutes. And then after that, we'll do some practice problems for circuit analysis. All right, so we'll stop here today and I'll see you all on Wednesday.